I bet that everybody here heard about eigenvalues and eigenvectors. True? Let's do a little bit of graphical intuitions. So, eigenvectors of a square matrix. Because the discussion of eigenvectors is I start with some direction and I see that I'm not rotating the direction. True? Let's look at this one. This is a very, very nice example. If I start with this one in the domain, in the codomain, what do I need to take? The domain means that I took E1 plus E2. True? That means the codomain, the Y, is going to be A1 plus A2. True? Are we together on this? In this specific case, we have that Y is AX, but is also actually 3X. True? So in a certain sense, for this specific couple, the rule simplifies quite a lot. Together? You see this eigenvalue, eigenvector pair? 1, 2, 3. Perfect. From a graphical perspective, you have 1 minute of finding the other one, another pair, with not 3 but another one, thinking about linearity, and you find it graphically, another eigenvalue, eigenvector pair. Go. Graphically. I'll give you an hint. I'll give you a hint. Look at this tessellation. This square goes into this tile. True? This square goes into which tile? It's -1, it's kind of a reflection, so it has to be this one. True? True? Perfect. This tile, where does it go? Think about this and then answer, and then you will see where the other eigenvector, eigenvalue finite pair is. Go. This tile here, it shares this side with this, true? And this side with this, true? You see, from the domain to the codomain, true? It means that essentially this side here has to be this side, and this side here has to be this side, true? Because I'm tessellating the codomain, true? You see? Perfect. It means that this point in the domain corresponds to this point in the codomain. True? We have x equals to y, or better, y is equal to ax equals to x. That means 1x. This specific one with 1 is another eigenvector, eigenvalue pair. Let's do numerically. Let's do numerically. How do I write the matrix given this stuff here? The matrix A is going to be 2, 1, 1, 2. And if I do this one times this point that is -1, 1, I get -2, -1 plus 1, 2. That means is -1 plus 1. How much are we together, people? 1, 2, 3. Excellent. Watch out. Watch out. This trick, that is a graphical trick that I'm giving to you right now, is something that is valid only for real eigenvalues. Whenever we have rotations, what do we have? I should have put the Mona Lisa. This is Mona Lisa starting and Mona Lisa ending. It's just a rotation. Do you see it? Do you see it? I do not know if you remember that whenever you got rotations, you got complex eigenvalues. Do you remember this? I was remembering it, never heard about it. I heard it, but I forgot. Do you see that square root of 2 over 2? I don't remember. Well, we have it here. We have it here. See that I'm dumb. If I know what I'm doing and I graphically visualize stuff, I find the values of matrix A by just looking at stuff. Write A in this case. It's going to be square root of 2 over 2 with the plus and minuses. A1 is first row, first column, true? Plus square root of 2 over 2 minus square root of 2 over 2, true? Second column is going to be plus plus. So the pattern, you see the pattern, is going to be square root of 2 over 2, and then it's plus 1 minus 1 plus 1 plus 1. True? Perfect. If you compute the eigenvalues here, well, we're going to see how to compute the eigenvalues. They're going to be complex. Here we were seeing that this direction was only stretched, and this direction was only stretched by the factor 1. True? Here we do not see anything graphically that only stretches. It's whenever we put complex numbers in, that means an R4 actually, then we see the only stretchings. Okay. How do you feel up to now, people? 1, 2, 3. Very much together, not at all, kind of. Interrupt me if you've got questions. Let's see. This one. Real. This means that it's real. Okay. Tell me. Don't ask me why. Just like this. Would you like to discuss people? Discuss people if it is not immediately clear. People, what would you say? What would you say, people? I would like everybody to answer. If I have this stuff here, it means that I've got a certain v for which I have that starting from this x, I go into minus modulus of lambda x. True? That is flipping along this, but there's also the scaling. Ax equals to minus modulus of lambda x, this says. If this is not clear, people, let's make it this way. If this stuff is not clear, you go back to 3 Blue and Brown and you rewatch that stuff there, okay? Perfect. Other questions?
Is there a connection between a negative eigenvalue and the negative determinant? So we also set that the entire
we are going to see how the determinant is going to be done very soon. Let's make just kind of a connection that is, I hope you remember this. If I take determinant of the matrix minus 1, 0, 0, minus 2, this one is going to be equal to, should remember how to compute determinants, product minus product, true, plus 2. Why plus? Because there's two flippings. The sign of the determinant is modulus of the rotations. Even number of rotations minus determinant, odd number of rotations, flipping, sorry, not rotation, flips, plus. How do we feel? Okay.